Thank you, Maria, and thank you to Hilda and the other Maria for inviting me to present this work. As Hilda said, the purpose of this work is primarily to look at ventilative cooling and if it's a renewable. Obviously, recently enough, it's been considered a renewable, but this particular assessment is to look at how we might evaluate ventilative cooling at the design stage and how we might consider it as a renewable at the design stage. The reason why we actually conducted this work is that I suppose, as Hilda mentioned a while ago, there's limited examples of limited adoption or practical adoption of ventilative cooling systems, and consequently there's limited examples of seasonal performance factors or efficiency metrics for these types of systems. And I'll explain momentarily what I mean by seasonal performance factor. The scope of renewables has typically been heat pumps, and in recent times we've been focusing a lot on heat pumps, and it's important to note that those who have come up with the methodology and calculation methodologies for renewable cooling have stated that they want to see renewables outside of reversible heat pumps. And for ventilative cooling in particular, they which kind of falls under free cooling in this definition, there was a few aspects that I suppose ventilative cooling had to overcome to be considered a renewable. And three of these are mentioned here below, and these are my interpretation of them. But effectively, ventilative cooling could not be considered if it was including passive cooling. So these could be attenuation or reduction methods. It could not be considered if it wasn't actuated or intentionally operated, which in some respect it excluded natural ventilation. But today I'm actually going to present an example of why natural ventilation should be included if it is actuated intentionally. And finally, then, one of the aspects of the renewable cooling definition that allows VC to be renewable is the exclusion of hygienic ventilation, and that is something I will also discuss as well. So the key metric that we're referring to is the seasonal performance factor, and it's effectively a ratio of the cooling energy supplied to a building divided by in most cases, the electrical energy that is used to operate the system. And free cooling systems are amongst the cooling systems with the highest seasonal performance factors. So that it's important that we assess these in the context of similar systems that are heat pumps, for example. And typically, when we refer to these renewable systems, and we use thresholds to determine if this is the case, and this is oftentimes specific to member states or depending on the actual primary energy factor of the country or the efficiency of the grid, particularly if you're using grid supplied electricity as your electrical energy input. And this can be different for different countries. In Ireland, this could be anywhere between 1.4 and 6 in terms of the necessary SPF to be considered a renewable, and can be as high as 9.5 depending on which country you're in. And so it was great to see that Venticool announced that ventilative cooling can be considered a renewable. I think we now need to start calculating ventilative cooling systems and simulating them and assessing what sort of SPFs they can achieve. Based on a limited review of the literature, we can see that this is great, because at the moment a lot of them would be considered renewables, or at least go in part towards achieving certain renewable percentages within countries. So this is great, but we need more work in this area. And so the purpose of the work I'm presenting today is to provide an example in a non-residential building where we assess the performance of a natural ventilative cooling system, or NVC system, and a mechanical ventilative cooling system in conjunction with an MVC system, so a hybrid ventilation scenario. To do this, I'll present a feasibility assessment, which is an approach we presented previously at the AIVC in 2023, and I'm happy to share that paper with people afterwards if they want to look at it. But today, the primary objective today is to look at the performance assessment using a dynamic simulation approach. And finally, hopefully, we'll discuss what implications this might have in the future for policymakers, but also for industry professionals. So the model that we developed was actually a model of a real building. The building is actually located in Cork. It's known as what's called a generic repeatable design. So this particular school, as shown here on the left, is actually located in multiple locations across the country. They use the same design for multiple schools in Ireland. So it's quite representative of what we call low energy schools in Ireland. We took one classroom, and with that classroom, we assessed the feasibility of ventilative cooling in terms of whether it's renewable or not. And we've done this with a simplified approach, kind of a cooling degree or approach. and I presented this sort of assessment previously, as I said, in the AIVC, so I won't go into much detail on that. But the main purpose of today is to assess, well, how might we look at renewable cooling in a dynamic simulation approach? And for this purpose, we looked at two strategies, and we looked at two different weather files. One is a design summary year for 2021, and the other is a design summary year for 2071. The actual classroom itself, you can see this is an example of the actual classroom. For our purposes, we simulate this classroom in Dublin, which is using Dublin Airport weather data. These are future weather files that were made by the Meteorological Service here in Ireland. And we use two approaches. The automated approach, which is a natural ventilative cooling approach, is where we actuate the actual openings, and those openings constitute about 7 square meters of openable area. And we actuate those particular openings using a control strategy and actuators. And then we adopt a hybrid ventilation approach where we have those automated openings, but also integrated into one of the openings is a mechanical ventilative cooling system. And this is an example of the system here on the right that we actually adopted in this particular case. Both systems and both strategies, were used during the daytime, but the hybrid ventilation system is also used during the night when appropriate. And so there's this great example here of trying to see whether we can get an SPF out of an MVC and a hybrid ventilation system. I just wanted to make a point here of our energy input values that we use for the seasonal performance factor calculation. We don't actually calculate these for NVC from dynamic simulation. We actually take a range, and I'll show you this afterwards, because there is very limited information from manufacturers on actuator energy consumption in dynamic simulation tools, and it's certainly a limitation at present. Whereas the hybrid system that we're talking about actually is available within IES, so this means that it's easy for us to see how much energy is being consumed. So in terms of our specific approach here, we calculate the Q supply. There's a few caveats to this Q supply. Some of them I mentioned previously. This Q supply excludes 8 litres per second per person with a maximum occupancy of 25, and some other aspects in terms of the control strategies for the systems themselves. In this case, we're calculating the SPF as an annualized number. So this means that whenever there is cooling, or whenever we consider cooling, we sum this up over the entire year, and the same for electrical energy consumption for this particular system, which is either actuator energy or fan power energy. So just in terms of, initially we'll just present the feasibility of this, and what we did was we actually, using RStudio, we produced a series of cooling demand data using a simplified cooling degree hour approach and a heat loss coefficient for the building, and we simulated kind of statically what sort of cooling demand we might expect in Ireland in various years. So from a current historical weather data set in 2022 as far up as 2050 or CP 8.5, which is the same weather file that Maria mentioned previously. But additionally to this, we also looked at the variance in cooling demand with different base temperatures. And because we're seeing now from the literature that there are examples emerging of base temperatures of 14 for low energy buildings. And while we didn't calculate the base temperature in this case, we did use the base temperature of 14 in a moment to present this specific seasonal performance factor. And it's important to note here that what we're seeing in Ireland is that the temperatures are increasing, the actual cooling demand is increasing by about 45% between 2022 and 2050 in the worst case scenario. But the change in cooling demand with the base temperature can change by anywhere by 575% between assuming a base temperature of 18 and 14, and I think this is important to note. So to do this is an output here of our static simulation kind of approach, this feasibility approach that we mentioned previously. And what we see here is that this is like an approach we would adopt if we were trying to assess what's the potential for a solution as opposed to how it actually performs. And in this case, we see that it's likely that NVC systems are going to get very high seasonal performance factor values. But this could vary because obviously natural ventilation is a variable with outside conditions. And then we have the MVC system, which in this case is getting an average SPF of 15, which again is quite favorable. And it would seem like as if the variance for that system is much lower, as it's just one ventilation rate we assumed. It's important to note that these values would be higher, but we removed 8 litres per second per person from our feasibility assessment. And this is something to note that in our previous assessment of residential buildings from the paper I mentioned previously, the actual removal of hygienic ventilation was lower than this. I think it was closer to 10 to 15%. So for non-residential buildings, hygienic removal might be a concern. So let's see what happens if we simulate it in the future. This is the outputs from IES when we look at the 2071 in Dublin Airport, and I suppose the first thing that's glaringly obvious to me is that there's limited overheating, and that these two solutions are clearly capable of reducing, of actually dealing with the cooling demand in Ireland. Maybe if we had urban weather files, it might be slightly different. But it's important to note that both of these systems are able to satisfy the cooling demand as was predicted. And I might spend a little bit more time on this particular slide because this is kind of where it all comes together. I present here two types of Q supply, and the reason why is because the maximum is what we expect to come out of the actual tool itself. But then you need to adjust that for ventilative cooling only by removing 8 liters per second per person. Additionally, those also have consequences for the E input, or the actual electrical input for ventilative cooling. And in this case, like 20% of the mechanical ventilative cooling system, or thereabouts, was actually considered as the ventilative cooling only energy input. And then for the NVC system, we considered a kilowatt hours kind of figure as a range from the literature. So anywhere between 1 kilowatt hour per meter square per annum to 2.4 kilowatt hours per meter square per annum. So the purposes of the SPF is just about VC only. I think that's important to mention here, that's what we did here. And additionally to this, it's important to note that like that particular reduction due to hygienic ventilation can, like as is shown in the feasibility stage, reduce the seasonal performance factor because we need to remove the ventilation aspect from it. But something to talk about, should we actually be including the hygienic ventilation if we are trying to cool a building, or should we remove it? The current renewable cooling definition suggests we should remove it. And this is more prevalent in the HVC system because the HVC system is providing less ventilation rate than the actual NVC system. And I suppose at the end of all of this, what we're seeing is seasonal performance factors that are based on thresholds from Europe and in Ireland that are compliant for an automated natural ventilation system that intentionally opens windows and intentionally cools buildings. And I think that's important to note here, that this system is a renewable and should be considered so. And even for an MVC system or a hybrid system and natural ventilation system, there's part of the year that this system could actually be considered a renewable. And I think it's also important to note that some of these SPFs that we see here are very much comparable with heat pump technologies that are already considered renewables. So this is how you might consider it at design stage. And you can see here that obviously our expectations and feasibility are not always met in design. And I think that's something that was mentioned previously as well, that we're at the moment, it's likely that MVC will still give us a renewable, but that the MVC system in this particular case, and this is one MVC system of a plethora of MVC systems, that this particular one did not get above 6, for example. Now, instantaneously, that can be higher, but I won't get into that for the moment. So what does this mean, I suppose? And I think this is where I finish up here with a few kind of thoughts of my own, and these are thoughts of my own. The ventilative cooling systems that we studied appear to be renewables, and the question I ask is, if grants are offered for heat pumps, why should they be offered for renewables? Something that probably we need to discuss further. And I think what we see at the moment is a lack of information from manufacturers on typical values you should use to calculate an SPF for a ventilative cooling system. I think that at the moment we're relying on dynamic simulations and we're relying on expertise in that area, whereas perhaps more product information should be made available for us to see whether a VC system is renewable or not before we even actually assess it. The other question I think here, and I think in the context of Marie's presentation previously, there's obviously going to be parts of the year where we won't use VC, and it's a cruel fact for some people that they won't be able to use it. But in some cases where the heating is reduced, the VC is improved. That's we're seeing that where there's more VC potential in Ireland in the future than there would be in the past, which is of interest where the shoulder seasons are getting warmer. And the question here is if the cooling season expands, what does this mean for grants as well? Like, are we only talking about May to September? For example. And I suppose just a few practical comments here before I finish up. I think we do need to see more examples from the real world, using real systems and providing evidence of the real performance. The best work I've seen thus far for this that actually assesses this using measurements is the work of Kramers using MVC systems, and we need to see more of this. And finally, I wonder, is there a discussion point around hygienic ventilation and whether we should consider hygienic ventilation removal as much as we have in this instance. For example, if we operate a system for cooling purposes and it also leads to hygienic ventilation, I don't know, is it fair or reasonable to exclude hygienic ventilation? And maybe that's a discussion for a later date. And with that, I'll now hand over the floor to Mana Sohail, who will be talking momentarily.